Hello and welcome to this episode in our series on NumPy. I'm very excited about the journey so far and I'm happy we are at this point. What makes this particular video exciting for me, and I'm sure for you as well, is about the fact that this is going to be our last video on NumPy, and the reason is that after this video you would have learned enough of NumPy to enable you to be able to build neural networks using the NumPy library. I am not in any way suggesting that these videos have made you an expert at using NumPy in any way, not at all. That is far from the truth. I don't know it all, and I doubt if there is anybody who knows it all. So what I basically do often is I Google things out and I read a lot from the Matplotlib documentation. So what I'm going to do in this video is I'm going to show you just enough of the linear algebra operations that are needed to build neural networks, and I'll end the series on NumPy, and then in subsequent videos I'll be explaining any NumPy technique that is new to you so that we can merge building neural networks and learning NumPy at the same time. So as always, I'm going to use an example to explain things to you, and what I want us to learn first of all is about transposing. Okay, so transposing, I'm going to run this cell. Let me just delete what is up here. Okay, so what is transposing? I'm going to use an example to explain to you, and I'm going to start by creating a random array. Okay, so I'm going to do ARR is equal to, first of all, let me import NumPy. I haven't done that, so import NumPy as NP, and I'll say ARR is equal to np.random.random, and let's say I want a 2 by 3 array that is made up of random numbers. So if I go ahead and I print array, you can see that this is an array with 2 rows and then 3 columns, and the items in there are as random as they could be. Okay, so what is transposing? Transpose is a basic linear algebra operation that turns the rows into columns. Okay, I am just giving you this basic definition so that it's easy for you to understand. There's a lot more details to the transpose operation, but I'm just telling you that the transpose for a two-dimensional array helps us to be able to turn the rows into the columns and vice versa. And you might be wondering, why would you ever want to turn the rows into the column and then the columns into the rows? It happens a lot in building neural networks, where you have to take the transpose of either the weight matrix or the incoming data feature vector, just so you can perform some particular calculation that you need to do, especially when it comes to matrix multiplications, which I will show you after teaching you about transpose. So the easiest way to transpose a matrix is to call ARR.T on it. And what's going to happen is, so initially we started with a 2 by 3 matrix, and see the arrangement. So 0.3, 0.6, 0.2, and now see when we call the transpose, you can see that the first row becomes the first column, as you can see here, and then the second row becomes the second column. So basically this is how we transpose matrices or vectors or n-dimensional arrays in NumPy. As to when you apply these, you would see it along the way when we start building neural networks, and I will do my best to explain to you why we need to transpose. It has to do particularly when you have to do matrix multiplications and then the dimensions do not match as required. Another way to do transposing is to call ARR.transpose. So there's actually a transpose function that you can call, and this is also going to transpose it for you. The basic takeaway from this section of the video is I want you to remember that for a two-dimensional array, if you call the transpose function on it or the T function on it, what you're basically doing is you are turning the rows into columns and the columns into rows. and it becomes particularly important when we have to do matrix multiplications, which happens to be the next topic of this video. So let's go, and I'm going to insert a markdown cell down here, and I'm going to give it a title, matrix multiplication. Okay, great. So now we're talking about matrix multiplications, and this is a fundamental linear algebra operation that we do a lot in deep learning. It happens to be the most frequently performed linear algebra operation in deep learning, because if you remember back from the earlier videos, I explained to you that what a neural network basically does is to find a linear combination. It performs a linear combination of the input features and some weights. Okay, that is where it starts from before the learning actually begins. And so a matrix multiplication is an important concept for you to understand. And I also remember I created a video where I showed you how to structure your data for machine learning. So if you don't understand why we have to talk about matrices, I suggest that you go back to watch that video, because it makes it clear why we need to structure our data, our training data, in the form of a matrix. Okay, now to help you understand matrix multiplication, I'm going to use some online animator that I found. Is matrixmultiplication.syz. Okay, so the first requirement for matrix multiplication to be allowed is that the number of rows, so you can see that over here we have 1, 2, 3, 4 rows, and then we have 1, 2, 3 columns, and then we have 1, 2, 3 rows and 1, 2 columns. What needs to be in place before two matrices can be multiplied together is that the number of rows in the second matrix should be equal to the number of columns in the first matrix. So this has 1, 2, 3 rows, and then the first matrix has 1, 2, 3 columns. The reason why this is a requirement is because of how matrix multiplication is performed. It is not element-wise multiplication where you are basically multiplying corresponding elements together. If that was the case, then it is impossible for us to multiply these two matrices, because if I multiply 2 by 1, 5 by 2, then what do I multiply with? 1 and everything on the third column. That is not how matrix multiplication works. And what if you are a computer science student, what I want you to understand about matrix multiplication is that, one, it is not element-wise multiplication, and it was created specifically to help solve linear equations that has many unknowns. And so it might not make sense why the calculation is done the way it is done until you understand how to solve a system of linear equations. But the takeaway I want you to get from this video is that the number of rows in the second matrix should match the number of columns in the first matrix. The reason is, if I want to multiply these two matrices, what's going to happen is I'll take the first column, I'll multiply it by every row, I'll perform a dot product calculation. And I also remember I have a video on dot product. So if you don't understand what a dot product does, then you have to watch that video to be able to go along. So I basically take this column here and I'll do a dot product between the column and every other row in the first matrix, and then I'll take the dot product between the second column and every other row in this matrix. So these people have an animation that I hope will help you understand things better. So I'm going to click on multiply, and you see that first of all it looks as if the second matrix has been transposed. So this is why I showed you how to do transposing before showing you matrix multiplications. It's not like you have to perform the transpose on your own, but the way matrix multiplication works is that you multiply, you perform dot product multiplication or a dot product calculation between the columns of the second matrix and the rows of the first matrix. So let's see what happens. So basically what's going to happen is that it takes the first, what used to be the first column of the second matrix, and it multiplies it with a row. Okay, so it is column wise, and then you multiply by the row, you sum it. That is what makes it a dot product. So basically you repeat this same process for all rows and all entries on the columns, and then you end up with your resulting matrix. And so what happens is, if I have, I'm going to use this as an example. We have a 4 by 3 multiplied by a 3 by 2, and so we end up with a 4 by 2. The whole idea here is, if you multiply an m by n matrix with an m by p matrix, then you get an n by p matrix as the resulting array or matrix shape. Okay, so now we are here. Let's try to perform some matrix multiplication. So I'm going to create I'll say A is equal to mp.random.random, and I'm going to create a matrix of shape 3 by 3, and then I will create B is equal to mp.random.random, and I'm going to create a 3 by 4. Okay, now let's see how, sorry, I need to make this a tuple. So let's see how we can do the matrix multiplication. It's as simple as doing mp.mathmul A and then B, and then you have to store the resulting array into another variable. So I'm going to print out C, and then let's see what's going to happen here. So basically I multiplied a 3 by 3 by a 3 by 4, and so I'm expecting a 3 by 4 as the result. So as you can see, we have 3 rows and then 4 columns. What happens if the sizes of the two arrays do not match? Let's say I'm trying to perform a matrix multiplication between a 3 by 3 and a 2 by 4. Let's see what's going to happen. So if I do a 3 by 3 and a 2 by 4, you can see that it violates the first condition I told you about. I said the number of rows in the second matrix should match the number of columns in the first matrix, and in this case the number of rows here is 2, the number of columns here is 3, and they do not match. This is the point where NumPy will not try to do broadcasting for you, because it is ambiguous and it can lead to subtle errors. And so they throw an explicit error. It says value error mathmul input operand 1 has a mismatch in its core dimension 0 with, I mean, these things can be hard to understand. That is why I first of all started by mentioning that you need to always make sure that your vectors or your matrices shapes do allow the performance of matrix calculation, otherwise it's going to fail. So I'm going to have 3 here, and then we are going to do the calculation. All right, now you might be wondering, at which point in a neural network's life do we use matrix multiplication? And like I said earlier, we use it many times. It is actually where we start. That is where the neural network starts its operations from. And the reason is that we need to do a linear combination between the weights of the neural network and the training data features that we want to use to learn the patterns in the data. And once I go back to the board and I explain how a neural network works, you're going to understand why we need matrix multiplications. But for now, I want you to understand how it is performed. Okay, great. So aside using mathmul, you can also use np dot. Okay, so you can use np dot to also perform matrix multiplications in matplotlib. In NumPy. And the difference between np dot dot and the mathmul that you have already seen can be in terms of performance for certain types of matrices, and also np dot dot, depending on the number of dimension of the arrays that you give it, it will perform mathmul under the hood, or it will just perform a dot product, as you know of. Okay, so before we start with performing dot product. Let me change this cell. Actually, let me insert call it dot product. Okay, so I'm going to show you what a dot product is. I already have a video that explains this, but for the sake of understanding, I'm going to do the explanation again. Let's say we have a vector of weight. So I'm going to call this weight. Let's say we usually initialize things to 0. So 0, 0. Okay. Let's say our weight vector has 0, 0, 0. And let's say we also have a feature vector which has the numbers 2.1, let's say 1.5, and negative 0.5. Okay. Now, what is the dot product of these two vectors? The dot product of these two vectors is just the summation of the element-wise multiplication of the items in the two arrays. And so it makes sense that the two arrays have the same number of items in them. So what's going to happen is we have 0 times 2.1 plus 0 times 1.5 times 0 plus 0 times negative 0.5, and I am sure you can already agree with me that the answer is supposed to be 0 because we are doing a summation of the element-wise multiplication of the corresponding items. So the way to do that is you say, let's say I'm going to say activations is equal to np dot dot, and then you bring the weight and you bring the feature, and let's print activations. Actually, I'll call it activation because whenever you perform a dot product, you are getting a scalar. So you can see that it is 0.0. What happens if any of the weight is not 0? Let's say this is 3.0, then you can see that basically because the other entries are 0, they cancel out everything here, and then it is just 3 times 2.1. So this is how we do dot product calculations using NumPy. And like I told you, you can also use the dot product function to the np.dot function to also perform matmul. Okay, and that is used quite often in deep learning. So we still have our A, B, and C matrices that we created up here. Let's see if we can do, instead of using np.matmul, we can use np.dot and give A and B and see if the answer is going to be the same. So I'm going to say D is equal to np.dot, and then I will want the dot product between A and B. And then let's print what's in D. And then let's see if it is equal to what's in C. And as you can confirm, they both produce the same result. Like I stated earlier, np.dot underneath behind the scenes actually performs matmul depending on the dimensionality of the vectors that you give it. So over here, because they were one-dimensional vectors, it ended up just performing the dot product as we know of. And because over here A and B are two-dimensional, it knew it had to perform the matmul operation instead of doing just a dot product. And so that is how come we ended up with it. So we'll be using np.dot a lot of the times more than np.matmul, but don't be confused when you see any other code on the internet or in a book using matmul. You just need to understand why they are doing what they are doing, and maybe the performance gains that they are interested in getting. Okay, so we are at the very last section where I'm going to talk to you about how to serialize your NumPy arrays. And in case you're wondering, why would you ever want to serialize your NumPy arrays, or even what is serialization? Let me start off by inserting a markdown cell, serializing arrays. Okay, great. So what is serialization? Serialization basically here means writing your NumPy arrays to file, to disk. And the question is, why would you ever want to write your NumPy array to a file on your hard disk? And the reason I can give you is that as a deep learning practitioner or as an AI engineer, you spend much more of your time preparing data than actually training newer models. Trust me, you will spend a lot more of your time preparing, cleaning up data, doing what is known as exploratory data analysis more than actually building newer models. And the reason is that the data that we have in the real world, or the data that is at our disposal as AI engineers, do not always come in the cleanest form that we want. And so after you have spent hours cleaning up these data, you don't want to repeat this task every time you have to work on that model. So the most important thing after you've done your exploratory data analysis, or cleaning up of your data, is to write it to disk, so that you can be able to read it back another time and use it for whatever purpose it is that you want. Okay, so I'm going to generate a big NumPy array. I'm going to assume that we have some real world data and we have spent hours working on it, cleaning it, and so we don't want to throw it away. What's going to happen here is we will write it to file and then be able to read it back. Okay, so I'm going to generate a huge data, and I'm going to call it dataset is equal to np.random.random, and let's say I'm going to generate 1,000 by let's say 50. This is not huge, but it's huge as far as all the examples we have seen in these videos are concerned. So now we have a matrix of 1,000 rows with 50 columns, and then let's go ahead and write it to file. That is as simple as calling np.save. They have save z and then save compressed, and if you read the information, the documentation that comes with it, you know what they both do. So the first parameter you need to pass to save is the path where you want the file to be written. I want to call this dataset.npy. Basically, we usually use the npy format. Some people also use npz, depending on whether it is compressed or not, but conventionally we use npy. So you just give it the path where the file is supposed to sit, and then the array that you want to write. So basically what this line is saying is I want to write the content of dataset into dataset.npy. So if I run this, it should be written onto your file system. And because I said dot/dataset.npy, it means the current, just write it into the current directory. So if I go to the file section of my my Colab interface, then I can see that there is a file here called dataset.npy, and that is basically how we save or serialize our data and get it stored on the disk. Now, the next thing after serialization is how to read it back, and so I'm going to insert a markdown, and then I'll say reading serialized array. So how do we read our serialized arrays back? Okay, it is also as simple. The same way NumPy gives you a save function, they also give you a load function, which takes care of all the details involved in reading the file back into an ND array. So I'm going to call it ARR is equal to np.load. And if you guessed, you're probably right. You just need to supply the path where the serialized file is. And so now, how do we know that whatever is in ARR is exactly what we wrote to dataset.npy? Well, we can check the shape. Okay, so if I say ARR.shape, at this point it returns an np numpy.nd array. So if I do ARR.shape, you can see that we started off by generating an array of 1,000 rows and 50 columns, and we wrote it to a file called dataset.npy, and we've been able to read it back, and now the shape matches. You can also check to see if dataset is equal to ARR, and this is going to be a huge thing. I mean, this is something you shouldn't do, because it's going to check for all of the entries, and once they are all true, you know that it is actually the same array that you are getting back. So thank you very much for being with me up until this point. I know you are itching to start building neural networks, but trust me, I have been there and I know what works. You don't want to jump any of these videos. You don't want to just start off by learning how to create neural networks, unless maybe some way, somehow you have understanding of all these things that I have treated in the previous videos, then that is fine. But if you are entirely new to the concept of neural networks, deep learning, machine learning, then I really entreat you to start watching the videos from the start up until this point. Have patience and learn little things one time, a step at a time. Do not jump. Otherwise, you will see that when things begin to get advanced, you will struggle with a deeper understanding that is needed to be able to engineer neural networks. Like I said, the reason why I started these videos is not because there are shortage of videos out there, but I just want to create a set of videos that I wish I had when I was starting out learning neural networks. And that is why I'm so passionate about the slow pace and the detailed explanations that I'm giving. My goal is that you guys who are watching these videos will become great neural network engineers or architects of neural networks, and have in-depth understanding of what you are doing, instead of just putting together neural networks using high-level libraries like Keras, PyTorch, and what have you. So thank you very much for watching and being with me. The next chapter and every other thing that follows this video is going to be hands-on, practical skills that you'll be learning about, and it is all about building neural networks. And we are going to start off by creating our very first perceptron to be able to separate or distinguish between two classes of data sets. Thank you for watching. If you've not subscribed, don't forget to subscribe and share this video, and I'll see you in the next episode.